All right, good afternoon. So today, as you can see, we are going to finish the hashing topics, and we started last week with a general overview with a few examples. So I will very briefly repeat what's going on, what we have seen so far. So there is typically, very typically, there is a table where we store our items which are stored somewhere in the table, and the question is of course is of capability of fast storing and fast retrieving items. And the general idea and the central idea is that each item has a position in the table, and that position is given by the hash function. Hash function. So hash function hf takes an item and calculates position, which very typically is an integer, not something else, but integer position, where you put 0, 1, 2, 3, and or let's say if you have n slots in the table, so that it is you assign to each item its position stored there. Typically, what happens are the collisions. When hash function of item 1 is equal to hash function of item 2, therefore item 1 and item 1 both want to be stored on the same position, and of course typically that is impossible. So what follows is collision solving or collision resolving collisions, as we see now on the screen. So there are collision resolution or resolving, and there are various possibilities. Some of them are listed on the screen. We'll see today additional possibilities, and after that we'll see how they are effective generally. So what's the main idea, of course, behind the whole table is that insert and find works very fast. If you have no collisions, then anytime you have an item, you store it and you retrieve it in the time which is proportional to calculating the hash function, the position of that item, and that typically is fast. And it is done in constant time, or it might depend on the length of item if the item is long. But nevertheless, from the point of view of calculations, if you can calculate the hash function of an item in constant time, then all the all remaining manipulation is done in constant time. Delete, that depends. Delete depends because typically if you just want to take an element and remove it from the table, typically that's not impossible because so I put there question mark, item might be part of colliding names list, so-called cluster, and just removing the item is not easy, because you would lose connection to some other elements in the table. So that's not easy part. On the other hand, there are many real-life situations when you don't need, in fact, do the deletion often. So you might live with it. Of course, the table typically is a fixed size. So if suddenly you have to process much more elements than the number you can accommodate in the table, then you have to create a new table, take everything from the old table, put it into the new table, and that again takes time proportional to the number of all elements you have. So those are two situation where the performance of the hash table is significantly slower. But nevertheless, on the other hand, in typical computer science trade-off, we have insert and find done very quickly. So of course that's good, and we cherish that. So now I'm going to go through the slides. We have already the general idea what's going on. Last time we have seen open addressing and linear probing, when we later arrived today to double hashing. I comment it as well. So let's go through the details in the slides. Mostly it will be either obvious, either easy to get based on what we already know. So let's go. I hope I can present it. So generally, the slides try to tell the whole story from the very beginning. So there are some motivational parts of it, very briefly told. So many applications. Why do we need any hash tables? Many applications require this. Typically, it's called a dictionary. And in the second half of the slide, there is a very short, simple example, which reminds us of standard everyday situation in any computing. Typically, when you write a code, you typically define some functions. Function f1, and then there is the code, then there is some function f2 with some parameters, then there are some variables x, y variable, then you say typically you do much more complex things. That is trivial example, and you say x plus y plus 1 or anything like that. So that is your standard code, which calculates whatever does it calculate. Now, so we say, okay, and so what? The answer is that typically your code contains a lot of identifiers of the variables and functions and objects you do define. Identifiers, and your compiler or interpreter. Compiler and or interpreter has to work with your code, and it has to compile or interpret the code in that number also. When it reads the input code, comes to a variable, it must translate it into some internal representation, For example, it has to know where the value of that variables are internally stored in the memory. So each variable and each function, each object is stored somewhere on some addresses, and in your code there are no addresses. So the identifier and compiler needs some dictionary where you input the identifier. Like here I have an example, sum. I have put there x and y and f1, f2, and it must, when it again meets that variable x equals again something, or x might be part of some expression. So it must go again internally and look for x in memory, what is there currently stored, just to be able to perform a particular statement. So it needs very quick and efficient access to all objects, variables, everything you defined in your program. Therefore, the hash table says, okay, I can typically do it because the items which we store in the hash table will be pairs. The first element in the pair is the identifier of your object, and the second pair is its address. So, and any time you want to talk about any variable, you say, aha, this is it. Compute the hash function of the string of the identifier, look into the table, and there in the table is stored, as it is shown here, is stored as the address, and your interpreter can continue its work. So that's and that happens a zillion times each day, because you write your code, everybody writes their code, and you have to compile it and do it, of course, quickly, and interpret it and do it, if possible, quickly as well. So that's important part of everyday manipulation of nearly any data. So that's just an example. Why do people come up with hash tables? For example, in a compiler, you needed them quite badly, in fact. Okay, so those are that's some kind of motivations. What the slides tell us next. Well, they just talk about the complexity. As you can see, the task which I've just presented with the compiler, you can say, okay, but we can build binary search keys. Yes, you can, and they are not that bad. So you can say, if we do the same with binary tree, you can do it, but it will be a little bit slower, and that little bit is enough to be, in fact, slower in a great scheme of things. Therefore, you say, okay, if you have binary search tree, it's fine, but getting to hash table is better. So on average, everything is except for delete. And for example, in this situation, you don't have to delete that much, because once there are some variables that you don't remove them suddenly from your program. So on average, constant complexity is fine. Okay, fine. So let's move to the next one. What, of course, happens is that nothing is ideal, even in computer science. So there are some necessary trade-offs between the speed and the memory usage. So typically, if you say, okay, we have a problem which users might use hash table, and if they give you infinite time, then there is no hurry. And if there is no hurry, so then you can say, okay, then we don't need a hash function. We just store our items anywhere, and if anybody wants to look at some item, then we can go one by one through our items until we find the item. So that means if we've got infinite time, we don't need an extra special ideas for organizing our items in the memory. Well, that's not realistic. On the other hand, there is another tendency which says, okay, and what if you have an infinite size of memory? Then you will say, okay, then we will not need hash tables. We will still maybe use some hash function, simply take each item and turn it into a number. You're going to imagine that you can take all possible items which might ever occur in any computer and just theoretically number them from 1, 2, 3, 4, 5, 6, 75 trillions, 85 billions of billions, and so on. So if the memory is infinite, you can easily create a situation where no collision occur, because each item, whatever can it be anywhere in the world, will have a unique, let's say, a number associated with it. So the number will be its address in your memory, and there it is. Of course, those two things, infinite time, infinite memory, never do happen. So now there is the pressure from both sides. You have not that much time and a little bit of memory. So what the result is the hash table with its hash function, and not only hash table size influences the search time, but of course also the strategy of collision resolution. Not only that. So then that's the topics of next half an hour. Yeah, as you can see, what they remind us, the constant expected time of a search and insert, that is good. Operation time is proportional to the length of key. Typically good hash functions, and we are interested in those hash function when there is some item. You might imagine that that item is, for example, an address of some computer in the network. So item, for example, AG some resource. This might be a unified resource locator of some page of a source. And that's a typical string which takes more than 10 and less than 1,000 characters, so it's about in tens or 100 characters long. And what you do, and we will do it in a moment, you take that item, that URL, and you scan it, or the hash function scans it character after character. So and builds, as it scans, it builds the value, the position where it should be in the table. So it goes once through the URL and computes the position. And there it is. So that's the only thing which takes longer, but you have to take in account the whole the whole string which you process, and there it is. The last part which they say here, hashing is not suitable for operations select, a subset, and sort. Typically, what is a subset, for example, not just subset, but range. What is difficult in hash functions is not easy, problematic, or hard, or not just impossible, but not supported. Let's say hash table does not support fast, does not support fast range retrieval. And of course, sub or sort elements, which is the same as the range retriever. That means all items in range item 1 up to item k, let's say, provided that items might be you can sort, or you can decide which of two items is bigger and which is smaller. Then you can of course think about some sorted items, but that they are stored in the just mostly as if randomly in the table. So there is no structure in the hash table which would support looking for item 1, like for example some I don't know, so for a particular item, and then the next item is somewhere completely elsewhere in the table, and there is no connection between them. So if you store a key like 577 in the table, it sits somewhere, item, and the next item 578 is who knows where after different collisions is totally somewhere in the table. So so that you cannot use your hash table for if you want to find a range between items. No good. So if you are going for one particular item, storing, retrieving good, that's a good job for a hash table. If you want to find a first third, give me 30 smallest elements which are in the table, in the hash table. That's not a good job for a hash table. So that's what they want to say on this. Slide, the next thing is that again there is more kind of reminders that the hash table is, when there is some hash table, is relatively small. It is a hash table which starts at which first slot 0 and the last slot is at 7,000 or something like that, while the number of possible keys is typically much more bigger. For example, if you can think of all unified resource locators, URL, or anything like that, which are in fact strings of length, let's say smaller than 500. So you can, anybody brings you any string, and that's some address of some resource. So you store it. You say, okay, we can store it in our hash table. And of course, those strings, no one knows how they will look like. So that might be any kind of string of any of those lengths. So the total number of such strings is about, now what is the total number? About, no idea. So let's say you have only American Standard Code for information interchange. There you've got about 100 printable characters. It's not exactly 100, it's 96 or so. So there are about 100 printable characters. Therefore, the number of strings where each character can be one of 100 possible characters, that total number is 100. that's a number of possibilities on one position in the string. The length is about the maximum 500. So it is about 10 to 100 to 500, which is 10 to 1,000. Yesterday they told me during the supper that the number of atoms in observable universe is significantly lower. Number of atoms in observable universe is about 10 to 75 or 10 to 80. I don't, and I quite doubt that anybody knows the figure exactly. So it is 10 to the 75. Which is that number, and the number of all possible characters is not 10 to the 75, but something like what 3 to like 10th power of that, or even bigger. So so it's huge. Obviously, and all we have at our disposal is a table which size is maybe 2 millions, or even if you go for big table. If your table is really big and huge table, hash table. So what? The size is megabytes, gigabytes. Let's say gigabytes in GB, in gigabytes. And what is 1 gigabyte? 1 gigabyte is 10 to the 9. 10 to the 9. 10 to the 9 entries, let's say. 10 to the 9 entries. And so it is pathetically small compared with all possible characters, or not just characters, all possible strings you can think of, and which might pop up there. So the universe of keys is terribly big. So the picture of this oval should be much bigger and stretch to the North Pole and to the equator on the other side, and maybe if it stretches to even to the moon, it is still not big enough to show how big that space of all possibilities is. And there is this tiny hash table which we use for mapping keys from that big universe into the table. So there is, of course, a thinkable keys, even if unused. Well, who knows which key will be used or not. So that's the main point of any hashing. So and then, of course, it is obvious that there very probably will be collisions, because when you have so many possible different keys, then of course some of them will want to sit at the same place in the table. So collisions are unavoidable. Now they just again what we have been talking about for already 2 hours. What's going on during the process of hashing? Take a key, compute its hash, its value of the hash function, and store that particular key, whatever might it be, or that item, store it in the table at the position which equals to the value of the hash function, as they say here. And then, well, of course, we have to resolve collisions. Now, all right. So now, okay. So you say, well, how do we compute hash functions? Now, in a little bit more detail, how do you compute hash functions? Again, they more or less give us a theoretical overview what might happen. So we've got these keys, which I originally called called items. Let's that be the keys. And we have the interval of addresses. That means the positions in the table. Those are positions or addresses. And from 0 to m-1, they use symbol m. I use symbol n. Does not matter that much. What are the synonyms? Synonyms are different items which generate the same value of hash functions. So there it is. So just reminding and what the hash function does. The collisions do occur. Now hash functions. Okay, so we can think about some hash function, but we demand from the hash function that it behaves nicely, that it takes that big, huge space of all possible keys and somehow maps them into the table in such a way that it approximates a random distribution. So, because if it is not random, then in a non-random situation, similar keys, or in some sense similar keys, might be mapped into the same slot, and that is a trouble. For example, if all addresses of anything which ends with .com would be mapped to the same position in the hash table, then of course, then of course that would be a bad hash function, because if everything which ends with .com is the same thing from the point of view of hash table, then of course everything will collide. So we want to simply take anything which comes from our big space of all possibilities, so that it appears somewhere in the table, and each one somewhere on some random place unpredictably. So you don't, in this way, you try to minimize the number of collisions. So of course the addresses space in memory, they want to say in table, are used of course uniformly. You don't concentrate most of your keys into some part of the table, because of course you want to use the whole table. It's tiny enough, so of course you want to. And this is nice, if that was possible, generates minimum number of collisions. How do you can assure that it will generate minimum number of collisions? I hope I will present an example where you will see that that of course it's very hard, but you are maximalistic. You say, well, that's what we want, and then you somehow try to set up your table and hash function and resolve collision mechanism. So this is somehow, at least theoretically, you strive to achieve that. So it says it uses of components of a key. Yes, surely, of course, if you store your if you store your keys, your items in the table only according to CTU to the last part, then of course you are in bigger danger that a hash function which takes care only of the piece of the whole item, the probability is bigger that there will be some collision. So obviously you should be able to use all components of the key, because if they are different, then of course you want to use the difference between two keys to generate the different positions in the table. So that you want hash function to do all of these, and all right, and then you say, well, and what are our items? we are storing in our hash table some items. That means our keys, which the function computes there. Its value of might be, for example, a real float values. Typically, that more happens in some engineering and scientific computing, where you've got some, I don't know, some temperature of anything, or maybe chemical composition or anything like that, which can be expressed in some real float values. Then you want to store float real values, and of course those are not integers, so you have to somehow make your hash function to reflect that fact. Integers, we have seen the example, so that should be easy. Bit strings and strings. Well, bit string is a strings of 0 and 1, so it is similar to string. It's a sequence of bit, or string is a sequence of characters or sequence of small integers. Typically is a string. That is important that those are sequences, not just one integer or a number. It's a sequence of characters, so those are different situations, and typically you don't have too much difference. If you've got some complex, if you want to store in your table some complex object which you generate into your programming language, then you have typically what you do, you turn that object either into string, either into sequence of bytes or bits. Well, it's in the memory, so therefore automatically you can interpret it as a sequence of bits. Then you can maybe interpret it as an integer, as a big integer number, or a sequence of small values, and that's therefore the situation where you have something more complex is typically covered by one of these four possibilities. One of those three last possibilities. So different key types and the examples. What you do if you store real values? If you have to store 0.537106818, I don't know, 0.0101 and so on, 04. I don't know too many numbers between 0 and 1, so I have to come up with some. Not easy, 4, 3, 4, and so on. So, for example, you want to store these things in your hash table. Where do you store them? You want to have a hash function. What hash function says? Okay, take some value k. For example, k equals to 100, and then take. That's not, that's M. And those are keys there, down there. What you do, you say, okay, multiply the key by 100 and then round it. So your table will go from 0, 1, 2, up to 98, 99 element or 99 slot, let's say, and then what you do is you say, the hash function will be what? Multiply by 100, it is 53.71 something, and round it, so that would be 54. 6.1 it will be 60. 201 will become 01, 43 will become 43. So now you have perfect, not perfect in the sense that it's easy to calculate. Now you've got addresses of those keys, and you can store them in the table at position 62. You store your 0.6118 and do everything else to the the rest of the keys. So of course, so what they say, it does not separate the clusters of similar values. Yeah, if you got 0.6181 or 619, they will go all into 62. So obviously there will be collisions. So maybe you have to think about some different representation. Maybe take them backwards. But again, that takes time. So difficult to decide what is the best. It's always difficult to decide what is the best strategy. Okay, so there you might have some integers instead of real numbers or floats. So what then you can do is to say, well, take your key divided by 2 to the power of w. So simply, how can I show it to you? Well, there are your all possible keys, and when you key multiply, well, if it is a w-bit integer, so k 2 to the power of w is bigger than your key, because key has w bits. So your integer k has at most w bits. So 2 to the power of w is bigger than k. Therefore, if you take k over now you divide it, so 1 is bigger than k over 2 to the power of w. So you've got some number which is smaller than 1, and of course it is bigger than 0. So it is, in fact, you can get to the previous situation where you say, okay, let's do this division either bitwise, either just to take and make a float division, get some result, and that is the value between 0 and 1, and then you just multiply it by m to get it into the table. So that's easy. Or just directly take your key and directly, which is fast as well, maybe even faster, modulated by your m. So if you have this integer key, that's what we have done so far in all cases last time. So if you've got m equals now the m, what should it be? I don't know, 277, 307, that doesn't matter. So then you say, okay, and then you take each k is, if your keys are from interval from 0 to 1000, then you take each key modulated by that and get the address of the table, which size is 227. Or as they say here, they can combine all previous methods in various ingenious ways. The more you combine, the more complex the function becomes, and the longer it takes to compute its value, and that means that it slows typically a situation, not just slows, computation slows down, so typically you don't want to go into them. So here they are just of some examples so you can think of, but you don't have to apply them. So first you round the number multiplied by something, then you modulate it, and so forth. These numbers which are here are just some examples of some, let's say, somehow maybe unpredictable number. The last one, take your key, take your k, that's your, take your key, and multiply it by something, so you spread all possible values of k, you spread them over much bigger interval, and when you modulate it by m again, you in fact the part in the bracket tries to behave the results more or less randomly from the standpoint of view of m, because m, let's say there is 0, there is not m, there is 1 times 1000. So if you've got any key, you multiply it by this constant. So you multiply, then you get to k times 16161. So there you get somewhere else completely. And then because you modulate by m, and m is relatively small, so m divides all this space into chunks of equal size, m each of them. So it is hoped that it is somehow more or less unpredictable where the value of function will be in any slot. Which is defined by value of m, and because you take modulo m down there, so the value of the function will be this is the value of the hash function of k, this size here. So you want to say, so if we make it more and more complex, it will be less and less predictable, therefore less and less random-like. Maybe, yes, but what is sure that the time you spend to calculate this will get a little bit longer and longer. Therefore, you can go and check other possibilities. This is very fast, but again, what does it mean? If you have any key, you turn it express into binary. In binary, which there is your key down there, and in binary it is some 1, 0. For example, there are some binary numbers, binary digits. There it is. So that's your key expressed in binary, and what the function does, it takes, take a -1, and when m is 2 to the power of x, then m minus 1 is only once, contains only one. So there in binary, m looks like this, m minus 1 in binary. And what you do is then you just add them logically. So in fact, that means that what does that mean? That you take just the last part of the key, and you totally forget the beginning part of the key, and you say, that's very easy to create some hash function. Of course, the keys which end with the same sequence of ones and zeros, they will produce the same value of a hash function. Now, what's going more in there? Examples, 4 strings. 4 strings. So that has to be again mentioned. Probably it will be the last complex part of this part. Yep. So how do you calculate a value of hash function for a string? First of all, you imagine that a string is in fact a sequence of characters, and each character is a number, is a small integer character. Typically, if you've got, where do I put it? Maybe somewhere down there. If you've got a string, it is a sequence of characters. So I will try to put 1 there. I say like simple one, like for example, take for example Bob. Yeah? So if you take Bob, though it's a sequence of 3 characters. Character B in ASCII is 66. 66. O is character, which number is? Now I don't recall, I remember M13 and O, it's number 15, I think. So M and O, yeah, 15, so 64 plus 15 is 79. If I'm wrong, correct me. And B is C. So you take a string and you say, okay, but in fact, it is a sequence of 3 numbers. Fine. And what you do with them? You say, and now you create a polynomial, and that polynomial is something like we have here at the bottom. And now just to create the function, you have some extra, only one. One is enough, you might have more, but one is enough. One additional number, which is somehow important. Typically, you want to be it a prime number, so we have this integer. And that says, all right, create a polynomial in which the variable will represent powers of that number we've got, and k2, k1, k1. Those the other number, the coefficients of the polynomial will be exactly the numbers which are here in the sequence. So in this example, we would have polynomial which says, well, take 66, whether you start at the beginning or at the end, it does not matter for computing, it does not matter whatsoever, and take your 1 and 27 to the second power, then add 79 times 127 to the first power, that means don't change it, plus again 66 and 127 to the power of 0 is of course 1, so you don't put it there. So you've got this thing, and it produces some result which I'm not capable of coming out from top of my head, which that might be. Anybody with a calculator might do it for us. And what is important now, so that is some value, no idea. And if you use a different string, let's take another string like Bob, and who is the other is Alice, let's say. If you want to code for Alice, what you do, this 8a is 65, L is, that's gonna be difficult, but not 65, no, we are gonna survive. L, M, and O, so the decrease by 3, 76, L, M, and O, yep, 76, I is H, I plus 9, plus A plus 60, 70, 3I, J, K, L plus 3, C is 67, and E is 69. So you go and calculate 65 times 127 to the power of 4 plus 73 times 127 to the power of 3 plus 67 times 73 to the power of 2 plus 67 times, no, 73, what, that's nonsense. Excuse me, this is 67 7 times 127 to power of 2 plus, I lost 67. That is 65. Excuse me, I am too close to the blackboard to produce it correctly. There is 76. Next comes 73. Then comes 77 times 127 plus finally 69. And again, when you compute this, it's relatively easy to compute the powers of 127, or you can of course have it somewhere pre-computed typically if you want to be fast, or you can use a Horner scheme down there, which will also speed up just the computation of this, of the value of this polynomial. Out comes the value, and that is your the value of your hash function. So having that is fine. You scan the whole string only exactly only once, and that is. You might say, all right, but as you can, when you look at it, there might be again just some collisions as well. And what about collisions? You say, well, what about the collisions? Maybe, how do you know that this value will not be the same as this value? Well, Alice will be bigger because it's obviously longer, and that's to the 4th power. But typically, you are taking and storing them in the table of limited size. Therefore, you will have to modulate the result by the size of the table, and it might easily happen that the two will collide. So, for example, another example down there in Java, this fixed number in Java. This A equals to 31. When you look into your Java source code, you create a hash table and or take a string and display a hash. It's called hash string, and there is this hash value or something like that. So then there is the function which is like this one, uses a equal to 1. So in that coding, Bob has a hash function of Bob is 65941. I didn't compute Alice, so excuse me, but the hash function of a completely different CQC equals also to 65941. So the hash function like this one, it again does exactly this stuff. It takes the input, computes the output, and it is bound to produce sometimes to produce the same results. But what is important that string is totally, not totally, but significantly different from that one. So if you put it inside Bob1, Bob2, or Bib, or Boob, or anything like that, it will be again different. So those keys which generate the same functions are in fact different and not expected to be easily in the same place in your input or close in your input, so you don't generate many collisions. So that's a standard way of generating position 4 in the hash table for strings. and it's probably the most fastest one. You might say, okay, and what if I don't go for this? For these powers which seem to slow down the calculation. If you don't go for the powers, then you will get each time you will get in fact very small values. So again, that big space which I mentioned here a while ago, again that will be squeezed into a very small space of just few hundred possible values. If you don't have a few thousands, let's say, few thousand values, and that means you will have much more collisions. So it is good to compute those powers. Now the next, so and you can do it, you can make it a little bit more complex, so I can just skip this slide because it says, okay, there is the scheme what to do. You can introduce another special value and use that value as well to again make that function even much more complex, therefore much more random, and again you lose some time. And as you can see, the authors were just playful because obviously they put there the values which you would probably not use in real life. That one is just a value of pi multiplied by without decimal, and this is now the value of e without the decimal. So they are just funny examples. So, and I will skip the rest because it does not help us too much. What is the final slide in this sequence? Says the hash function returns often the same value. Of course, yes, that's the problem. Wrong time code generates many similar addresses. Yes. If you don't put the powers there, you will generate many same addresses. If you consider only 3 or 4 last characters in long strings, you will generate many similar addresses. And of course, then anything which runs above your hash table, because those are support structures. Hash table just is a storage for data, so it is used by your application which does some real job. And then, of course, you are dependent on the quality of hash table. And if for any key you have to search a lot of elements inside the hash table, then you lose that primal importance, primal advantage of a hash table, that it is fast, so then it becomes slow. So it is expected to be fast, but it depends on correct and nice hash function, and nobody in the whole world can tell you what exactly in your situation should be nice and effective hash function. So it is a two-sided story or two-sided coin. On the other hand, if you manage to have the good hash function, you are fast and perfect. If by some chance a hash function is not good, if just by chance you generate your items are such that hash function generates the same value, then of course everything goes out of the window. So now let's talk about the collision resolution for remaining 20 minutes. We have seen a linked system or chaining, so-called, where each colliding element is put into a list which is adjacent to a particular slot in the table. So here it is very similar. You modulate by 3, which you would not do in real life. So modulate by 3 the key, and 1 is where is 1? There is 1. 5 is there. 21 is there. And now when comes colliding element, which is 10, which modulo 3 is 1, the same as 1. So you take and insert that element, that colliding element, in front of the list, which which corresponds to the position. The same happens with 7. 7, you take 7, and what you do, the remainder is again 1, so you put it into the same list, and so on. So the list again is might be possibly long, but again you don't want that, because then of course the hash table loses its sense. So you will need a longer hash table, and again good function. So next. There is just there are just codes of the function. They are, strangely enough, they are not in Python, which we use an official language of this course. They seem to be in some C++-ish, Java-ish manner, and we can skip that easily, because the idea of all the stuff we are talking about is very simple. So just initialize, make all nulls, and then of course insert, you just insert into a list. So that's relatively easy. What is then? But there are some important notions. There is so-called load factor. That is why it is red. Load factor is an important parameter of any hash table. So we haven't talked about it yet. And obviously and intuitively, it will be an important one, because it just tells you how many elements, how many items are there stored in your table. And what is important is not that absolute number, whether there are 200 or 35 millions, but its ratio of the number of elements stored in your table to the size of the whole table. So if it is full, 50% full, 90% full, 99% full, or something like that. So the load factor tells you how densely populated the table is, and that's important, of course, because obviously, if it is densely populated, then the probability of any collision is bigger as the load is getting close to 1. So if it is nearly full, if it is full, then there will be sure a collision. So on average, what is the cost of insert? Well, you put and insert it into when there is this chaining system. You take anything additional and insert it there. So you immediately can insert an additional element into any list. So therefore, it does not depend on your load. And search, well, search is something like this. So again, you can see alpha is a number which is it's nonsensical. Alpha is number of elements. M is smaller than n. Therefore, this should be reversed. M is smaller than if you have yes, this is correct. Excuse me. Yeah. So if you have 2 times as many numbers to store in your table with chaining, then you will need on average 3 accesses to look for an element. Deleting is simple. Again, it is the same as to find the element. Well, when you find it, you just remove it from the list. So that's the same. That's the same story. This alpha will pop up in the next strategies of collision resolving as well. So let us go and see what's going on in there. Excuse me. So of course, you don't want the load factor to be too big. Rather obvious. So the second part of the slide is also relatively simple. There is this this plus, which says, okay, the size of the table does not matter that much because you can extend it to the right by appending elements into the lists. But on the other hand, what they say there at the bottom, of course, is related to manipulating the memory and working in memory in the background. So that takes, of course, additional time and memory as well. So it's, on the other hand, it's some kind of minus. Again, who knows whether it is good or bad? Depends on your particular problem. And the next part we talked about yesterday was open address hashing. And open address hashing says, okay, we don't have anything outside, everything is in the table, and we store everything inside the table. So when there is the collision, we apply so-called linear probing and next double hashing. First, talk about linear probing. And linear probing does the following. As you can see, what happens when there is a collision, you move the colliding elements a little bit further down in the table and leave it there. So let's jump into it, because there is nothing too much of a new. The collision does not distinguish anything. Search hit, search miss. Search, it's rather obvious, so I can skip it. Linear probing, what does linear probing? When we are colliding, as you can see, when we collide, we move the element to the next slot. Or we can move that element each time by 2 slots forward, or each time by 3, or by 17, by any value which somehow is not has we can move forward by any number 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5. So if you, after collision, if you move by 2 steps forward after collision, move by 2 slots forward, so what would happen? This is not a good strategy. If you have a collision at this position, then you will move by 2 slots forward to the next position, then you will move to the next position, and then by next 2 moves, 1, 2, you will arrive back where you have started, and you have explored just not all the elements in the table. So the shift and the size of the table, greatest common divisor of those should be 1. So they should be coprimes. That's important. Otherwise, you get into something you see here. So you move forward in linear probing. The hash function reflects that thing. What is that I? That I is the number of collisions we meet when we are inserting or looking for one particular element. That is the one particular key, which is denoted here by K. So K modulo 5 plus E modulo 5, or you can simplify it to that, where I is this number of collisions. So at the beginning we have no collision. If collision appears, then you go to K plus I and modulated by 5, or K times I might be multiplied here, which would be by 2, by 3, by 78, or anything like that. So that I is increased, as they say here. And that's the whole linear probing. Here they just repeat it and repeat it when you are trying to insert 10, which belongs to position 0. So here everything is full. You've got a nice, in the sense of pathology, cluster, but and of course it's an annoying cluster in real application. There is a cluster, and you have to move through that cluster nicely and see until you find an empty space, and finally store it there. So the value of I is finally 3 when you get to finally the first free position. So that was open addressing. Sorry, that was linear probing. And open and double hashing is very similar to that. Double hashing, sorry. Linda, again, I will skip the code for that because it's just going through one-dimensional table. Anybody, I hope, can imagine that that code contains nothing, no surprise, so I can easily skip it. Now, quickly, what is important? Well, we jump to double hashing, and double hashing is called double hashing because there are, in fact, two hash functions, not just one. Two hash functions merge finally into one hash function, but two main components of the hash functions which do cooperate. First hash function is your hash function, that's the function which is there at the beginning, and the second hash function kicks in only when there is a collision. That is why it is here multiplied here by the number of I. That's the number of collisions. So what's the idea behind? In linear probing, after each collision, we apply absolutely the same strategy with no change. We absolutely rigidly all the time. We try to move forward, find the first empty slot. We find it, and there it is. We have found it. But what we want is to have a function which disperses the keys regularly, uniformly, and randomly across the table. Therefore, you might say that we will improve our strategy in that for a particular key, for different values of keys, the shifts by which we move forward when looking for an empty slot in the table, those shifts will be different, and they will depend on the values of the key, of course. So that's the second hash function, and the second hash function says, okay, when there is a collision, I will take care of searching for the next free space. So that's the gray part, and I don't know what is this. This is there just to be each key has different pro sequence. That's the most important story there, and then there are examples, and we'll see examples during the practices, so we can easily skip this. What the most important statement is that one on the right, that different keys have different probe sequences, so you don't apply the same strategy to each key, which increases your chances of reducing the number of collisions and clustering and such. There we are. How does it look in practice? Again, very short. Let's take an example. 1 is already there, 5 is already there. What you do with 20? 20 wants to sit modulo 5 at position 0, but it is colliding. So you take second hash function, take the same key, which is 20, modulate it not by 5, but by 3. That gives you sample. No one what value will be. 20 modulo 3 is 2 plus 1, because you want to have a shift at least 1 each time, so that 1 has to be there, and you've got and you move by 3. If you were trying to insert not 20 but 10, 10 would have also collide at the same position, but the second hash function will generate a different shift, namely just only 2. And if you try to insert 30, then 30 modulo 3 is just 0 plus 1 with 1, so 30 will have just one step 1 as moving forward. So again, you can, at the position of the second hash function, you can again imagine something more and more complex, but again, you want to keep it simple, and this is rather relatively, turns out to be relatively nice. Nice approach. Which does not take too much time, and it disperses the keys along the table quite nicely. So that's the idea of double hashing, and the example continues because they want to insert 25, and 25 is inserted immediately? No, because it wants to sit modulo 5, wants to sit there. And again, the second hash function says, okay, we've got collision 25 modulo 3 is 1 plus 1 is 2. So therefore, 25 appears there where it appears in the table. So that is just to disperse the values more and more when they collide. And so on, the example continues. There is nothing strange about it. Of course, it was constructed to show that when you take another special value 18, again, the value of the second hash function will be different, so it will jump somewhere else and find quickly the free slot in the table. So and after that you see, and what they want to suggest that double hashing somehow makes less collisions in some typical setting, which is more or less observed fact that double hashing is better than linear probing in most practical applications. Although, of course, you can easily construct again an artificial example where double hashing will totally fail, but those artificial examples do not happen too much. So what will they might conclude about it? I want maybe to show you some table, which let's jump to that table, because the rest is about deletion, into which we don't have time to go into. So in the remaining time, I will skip the codes, which again are the same codes you might expect as in the previous example. So I will skip them and jump into final conclusion, where we remind ourselves that there is a load factor. In this case, the load factor is less than 1, because we have one table and everything is inside a table. So what's there? You say, well, okay, the number of items is smaller than the number of the size of the table. So that's the load factor. And what are the conclusions? Are these ones? Maybe the next one shows it once more. First of all, let's start here. There are some formulas which you can derive if of course you have to suppose that all the keys you are using are uniformly dispersed in the whole space of all possible strings, and that they come randomly. That you randomly take a random keys after random key, and you store them in the table. So which might be and might not be realistic, but nevertheless, what you can expect is that there are some formulas which tells you how many search hits and how many search misses will be there, hits and misses, when either you find the key, typically you find it earlier, or when it is not there, because when you come to when you look for something, looking for a key, it is not in the table, but the key still generates a a collision, so you have to go through the whole cluster, and only when you are out of the cluster you conclude that the key is not there, so that takes a little bit more time. Which yeah, this is positive. Sorry, it is bigger than 1, of course. So, I mean, this is smaller than 1 after. So, if you multiply it, you multiply it by something bigger. What does that mean? That we've got some formulas, and all we have to do is to plug some load factors into formulas. So, load factor might start relatively small populated table. Half of the table is populated up to 90% populated table. And how many elements do in the table? These are the absolute values. How many elements do you have to probe in the table? So if your load factor is 3/4, you are using linear probing. That on average, if you are looking for the keys which do exist in your table, you will each time visit 3 elements. Now, what is absolutely important in this table and in this conclusion, and it is not on the slide, is that these values do not depend on the size of the table. So it doesn't matter if your table has 20 elements or 20 billion elements, does not matter. What is important is just the load factor, and you say if that load factor is this, you expect this number of accessing the table. That means with any one item, that means checking that number of collisions, let us say -1 +1 or something like that. So that's, as you can see, that's the most important finding which we will today end with. The effectivity does not depend on the absolute size of the table. It depends on the load factor of the table when we are using this linear probing or double hashing. And that's relatively, that's all. You can see that the number in the second table are smaller than in the first. So double hashing, when you are 3/4 is your load factor. So the worst that happens is still rather very, very benign, and search is missing. Those are different values. I remember there was some small typo somewhere in this table. So anybody who wants to check these values has to themselves plug the alpha values into these formulas to get the values in the table. So one is something maybe it's not there 1.6, maybe it is 2.0, something like that. But nevertheless, generally the tables are correct. So that's the conclusion. So we have seen quite a lot. So from now on, if anybody brings you a hash table, you might say, "Oh, I understand everything, what's going on, how the function is computing, how there might be various ways to resolve the collisions, and they are not all possibilities. There are zillions of other possibilities how to resolve the collisions, but we don't have time to go into that, and it would need a special lecture which we don't have a space for." So thank you for today, and see you on exams, I think.